and good afternoon or evening for the ones who are joining us from outside. This is the fourth session of the O'Higgins Seminar on Optimization, and today we're very pleased to have with us Jiang from Hong Kong's University of Science and Technology. And today he will be talking about his work titled Scaling the CVaR Approximation for Solving Change-Constrained Programs. Thank you very much, Nan, for being here, and you can start.
Thanks, Claudia, for inviting me. And hello, everyone. Good morning. I'm very happy to be here to talk about my recent work on change-constrained programs. I started this job 2 months ago. Before that, I was a postdoc in Cornell Tech, and Ray was also a postdoc with Andrea before. And then we started to talk about something about the change-constrained programs, and then we have some idea about how to do some new stuff in the change-constrained programs. So today we are going to talk about this work. And before that, we are going to provide you some literature review on change-constrained programs. So the change-constrained programs today we are going to focus on has a very general form. It has the objective function 3 transpose x. It can be any objective function, but linear objective function here is just a notation. And the uncertain parameter psi here. And the uncertain parameter also have the corresponding uncertain constraint, and function g here denote the uncertain constraint. So this uncertain constraint has to be satisfied with probability 1 minus epsilon. Epsilon here is a risk parameter. And the change constraint is only one part of the constraint. The other constraints are deterministic, and which are summarized in the set X here. So this is a very general form. This is the change constraint programs we are going to talk about. And for presentation purpose today, we are going to focus on the discrete case. So that's to say, we are going to have the indicator function here, and we are going to have n scenarios. If this scenario is satisfied, that this indicator function value will be 1. And then you can say we're going to, the probability, this constraint is satisfied with probability 1 minus epsilon. That's to say we have n scenarios. We have n scenarios. We are going to satisfy n times 1 minus epsilon part of them. So this problem has many applications. I can give you some examples here. For example, the wireless communication networks. Right now, I'm in my office because I want to make sure the internet is strong enough that you can hear me with a high chance. So I don't need to worry too much about the low internet speed. And the power system is also another example. You can see the renewable is random. So we want to make sure that we can use change constraint to make sure that there's a little chance the system may face the blackout. And the portfolio selection is another example. We know the return is random. So we want to make sure that there's a little chance maybe we are going to face the significant losses. So hopefully I can convince you change constraint programs have many, many applications. But our focus today is to say, actually, this problem is very hard to solve. And let's look at one simple example. If we have the constraint is the linear constraint, and we have 3 samples, they sample with equal probability. So we can write down this problem in this way. So the epsilon here is 1/2. That's to say we're going to satisfy at least 3/2 of, we're going to satisfy 2 of them. So is which 2 we should satisfy? And we can draw the feasible region of these very simple change constraint programs. And the upper half space here is to show that this constraint is satisfied. So this is the first constraint. We have 2 more constraints. We can draw their feasible regions for each of the corresponding constraints. And then we are going to choose 2 of them. And we can see that the upper half space of the red curve is the feasible region. And this feasible region is non-convex. So to handle this non-convexity, we're going to focus on 2 parts. One is the better convex approximations. Another is maybe we're going to, because this problem is a MIP, maybe we can use fast exact method. How we can speed up the exact method. So we're going to first talk about the better convex approximations. And then let's look at some literature reviews. What are the convex approximations for change constraint programs? And the first of all is a very famous one. It's called conditional value at risk approximation. It was proposed by Professor Nemlowski and Professor Shapiro in 2007. And this is also known as the CVaR approximation. And there's another heuristic. We are going to name it as also X. And when Claudia invited me for the talk, maybe original idea was to talk about this research. But later on I say, okay, I have another recent work. Maybe I want to talk about that. So I'm also going to review this work. This is a heuristic which was proposed in 2017. There are also other probability-based approaches. So let's first look at the CVaR approximation. What is the CVaR approximation? So we can write this chance constraint this way. Previously, we have the less than or equal to and the greater or equal to 1 minus epsilon. So we just flip the sign, and then we're going to use the violation. So that's to say their total violation should be less than or equal to epsilon. And we can draw this indicator function. If this function is positive, that means this constraint is violated. So as clearly this problem is non-convex. So how to convexify this this indicator function? A very simple way is to choose a negative point here, and then draw a line from this point to the 0, 1. And then this line can be denoted in this way. And we can replace the indicator function by using this function, and we can write down in this way. And this is exactly the form of the CVaR approximation. This has a CVaR corresponding formulation. So this has been shown to be the best convex of our approximation of the indicator function. This is the result in 2007. So we can look at one example of what is a CVaR approximation. Let's still go back to our previous example, and we know this is the non-convex feasible region. And right now what we know is CVaR is a convex approximation. So what it will show is actually will replace this non-convex feasible region with the convex feasible region right now. But as you can tell here, this is suboptimal solutions because CVaR approximation can be conservative. So after this paper, there are many papers is talking about how to improve the CVaR approximation. There are some different methods like the DC approximation. We are not going to talk about those things. We are going to look at another heuristic which was proposed, which is right now called also X. So back to 2017, Professor Ahmed, Professor Ludwig, Professor So, and Professor Xie, they have one paper. In their paper, they call it a heuristic. This heuristic has a bilevel structure, and we are going to talk about what is the bilevel structure here. And at that time, they just provide a heuristic. But later on, when I start my PhD, I start to look at this heuristic, and with my advisor, we actually renamed this heuristic as also X. The idea is to say this is also excellent. So we are going to show you why this is also excellent. So the basic idea is like this. We are going to guess a bound for the objective function C transpose X, and then we are going to solve the minimization problem. So what's this? It's actually, we are going to guess the T here. This is the random bound right now. And then we are going to solve this kind of the problem. For each constraint, we are going to have the S value. S is non-negative. And then we are going to take their, you can think about S is the violation. And then we are going to minimize their average violation. This is for a given T. And then after we solve this problem, this actually can be, this is from their heuristic. But actually we can also project this S out. If we project this S out, the idea is like the hinge loss. Is we are only going to focus on the positive truncation. These two are equivalent. The S is the auxiliary variables we just projected out. So this problem is actually from their heuristic, it has a very nice interpretation. It's for the given T, for a given bound, we are going to solve the average violation problem. And then we are going to check the feasibility. If this X hat for the given T is feasible, then we are going to say this constraint is satisfied. And we can use a very simple binary search to update the bound T. So the idea is like this. We are going to solve this problem first with the given T, and then we are going to check the feasibility. If it's feasible, we are going to decrease the current bound. If it's not feasible, we are going to increase the current bound. And then we can repeat this procedure by using binary search. So this is the idea back to the 2017, the heuristic. And when I start my PhD, what I did is I started to try this heuristic to say what is the performance of this heuristic with CVaR approximation. And let's look at a very simple example here. We still have three scenarios here, and x greater or equal to 3, x greater or equal to 2, and x greater or equal to 1. And very simple, you can say this problem, if you want to satisfy two of them, and the optimal solution is 2. So this simple example, the CVaR approximation is 8/3. Because it's a one-dimension problem, we can find the closed form very quickly. And even in this very simple example, you can tell CVaR is kind of suboptimal and very conservative. So we start looking at, okay, what is the performance of the also X of this heuristic? We can write down this, solve the lower level problem, and then for the given t, we can check the feasibility. So what we can do is we can start with the given t first. We can start with any t, but maybe we can start with the CVaR here, or any value that is greater or equal to 2. So if we solve this problem, we notice that we solve the lower level problem, then only S1 is positive. So only S1 is positive, that means this is a feasible solution. What we should do is decrease the current bound. We're going to decrease it, and until it is 2 in this example. So in this example, what we have is the V star can be recovered by using also X. And this is better than the CVaR approximation. So later on, we try to generalize this condition, and we say, okay, actually, when function g is convex in X and the set X is convex, this is the only condition we need. And then by using this condition, we can show that also X can provide a better solution than CVaR approximation. So the proof idea is we use the primal dual. That is why we have the convexity here. The only thing we need is a primal dual. So what is the literature tell us is also X is also excellent. It can outperform the CVaR approximation in this kind of the bilevel structure. So, but also X is not the best one. Let's look at one simple example. Still our previous example. What will happen is, if we solve this problem, this is the very first example. We are going to encounter one issue is for the given t, and then actually this nice segment, all the solutions are optimal solutions. But you can tell the point B is not a feasible solution. Then we are going to increase this value until the CVaR solution. So the idea here is to say also X even though it's better than CVaR approximation, but it still can have the same solution as the CVaR approximation. But what we can observe here right now is the CVaR and also X, they are all based on they are not based on original indicator function. They are based on the values. The value here actually matters. The constraint values actually make the difference. So hopefully I can convince you right now, you can have a feeling is instead of considering the original indicator function, this is non-convex. But right now, these convex approximations, they all somehow use the values of the original constraint, this information. So then we are going to think about one question is, the value of the constraint will make the difference. But if we do some scaling of the constraint, will they change the optimality? Will they change those kind of approximations of the chance constraint programs? Because we know if we have the alpha here, alpha, let's say, is some positive values. Whether alpha is 1, each alpha is 1, or each alpha is 2, or maybe some combination 1, 2, 3. Because we have the indicator function here, this will not change the optimality of the chance constraint programs. And then Ray and I, we start to think about, okay, will this change the optimality of the CVaR approximation? So we start to write down this paper, and this paper right now is under the R&R at Operations Research, and we are still working on the reversions. But this is a very simple motivation. Well, maybe 1 year ago, when we think about this problem, and then we start to look at, okay, because we know from our previous examples to show that the value of the constraint actually matters right now. But actually, we don't know whether this will change the optimality of the CVaR approximation of any kind of the convex approximations. So, but we still have the previous example. We can do a very quick numerical study to check. So what we can do here is, okay, we write down the CVaR approximation in the kind of extended space. So we write down all the variables right now. And what we can do here is we can scale some constraints. So for example, the first 2 constraints, we can put the alpha there. And you can say whether alpha is 1 or 2 does not change the optimality of the original chance constraint programs. But right now we can have the alpha in the corresponding CVaR approximation. And here we call it the scale CVaR approximation. And this is a function with alpha. Alpha right now we can say it's a given number. We just want to show what is the effect of those alpha, how those alpha will impact the CVaR approximation. So we can draw a figure. So this figure is how to interpret this figure. So when alpha is 1, that is the original CVaR approximation. So we know, okay, this is 2/3, and the optimal solution in this problem is 1/2. And then we start to increase the value of alpha. So when alpha is actually increases, you can see this objective value of the corresponding scale CVaR approximation actually decreases. And it's well close to the optimal solution in this simple example. Then we start to think about, so two things. Different alpha indeed will change the optimality of the CVaR approximation. The second thing is it seems like it may provide us with an optimal solution in some sense. So then we start to generalize these conditions. That is the things we work on, mainly work on in the last year for this work. So let's formally define some mathematical notations. This is the original CVaR approximation. Right now we have the scale CVaR approximation, and right now this alpha we are going to say is a decision variable, and we make this problem to be the bilinear problem. So alpha here is to scale down on the original constraint, is to say whether the original values will matter right now, and we put alpha is greater or equal to 1. This is kind of like the normalization. So we can also put other value here, but to put alpha is greater or equal to 1 is mainly on the normalization part. So right now this problem is a bilinear problem, but we want to show what is the formulation, what is the powerful of this formulation. So very clearly we know that the scale CVaR will be better than the CVaR approximation, because when alpha is 1, it will be the recovered original CVaR approximation. There are also some studies on the scale CVaR approximation. First, back to the 2010 paper, this is the maybe earliest work we can think about in the literature. And this work actually tells us we can scale the CVaR, and this can provide us with a better approximation in the joint chance constraint programs. And those two papers actually from the Professor Daniel Kuhn's group, they all focus on the distributional robust chance constraint programs. And then they have some benefits there for the corresponding scale CVaR approximation. But none of the paper try to answer this kind of the question is, what is the relationship between the scale CVaR and the original optimal solution? Is it possible we can provide some conditions such that the scale CVaR actually is equal to the original problem? So we provide two conditions, and the first one we call it a very general condition, and those two conditions are enough to show that based on these two conditions, the scale CVaR approximation will return an optimal solution of the chance constraint programs. So later on, I think maybe in the last slide, we are going to show you these two, we are going to discuss on these two conditions. But right now, these are the only two conditions we need, and these two conditions actually are tight. So the first condition is to say, if the constraint is satisfied, so we hopefully is strictly satisfied. And the second condition is n times epsilon is not an integer. We still have some margin here. We are going to discuss those two conditions in the next slide. Maybe right now you feel those two conditions are too restricted. So how can we prove this result? The only thing we are going to show here right now is to say, okay, these two problems are actually equivalent. So to show the equivalence, we are going to do the proving this way is we are going to show two directions. So one direction is easy because for any alpha here, we are going to have the corresponding CVaR approximation, and we know CVaR approximation is the upper bound for the original chance constraint programs. So this one is straightforward. And another side is slightly challenging. So what we do here is we actually do the construction proof. So we let X star to be an optimal solution, and then we actually can construct a feasible solutions such that this feasible solution is also feasible to the scale CVaR. The construction is something like this. The first thing we do is we actually split the set into two parts. One part is the set is strictly satisfied, and another part is the set is not satisfied. And then we define the alpha bar to be the kind of the margin. And then we are going to scale each alpha. If it's not satisfied, if it's not satisfied, we're going to if it's satisfied, we're going to scale it corresponding alpha. If it's not satisfied, we're going to set alpha to be 1. And then based on this construction, we can show that this is the feasible solution to the original. This is a feasible solution to a corresponding scale CVaR approximation. And this is a very simple proof based on our observation. And this actually tells us the scale CVaR, and it's possible to do the scaling in the CVaR approximation to recover the true optimal solution of the original chance constraint programs. So we have two conditions. Let's discuss them one by one. So the first condition is to say the constraint G, if it's satisfied, it should be strictly satisfied. So that's to say we should have something like this. And this condition is a condition actually also proposed by Professor Daniel Kuhn's group. They have the similar condition in their 2017 paper, I guess. Yes, 2017 paper here. And we can give you a very simple example to say if function G is the joint chance function programs, and Kasai is sampled from the integers. So you can say Kasai here is an integer, and then X is binary, and then we can manipulate the B to not be integer. And then this condition is always satisfied. And this condition actually can be relaxed when function G is convex in X, and we have the convex at X. We're going to discuss in the next slide. Another condition is n times epsilon is not integer. So this is also easy to manipulate because we can perturb the value of the epsilon, and this will still preserve the optimality, preserve the optimal solution of the original chance constraint programs. So for example, here you may be curious about why when I started the presentation, I used the 1/2. I didn't use like 1/3. So here is the answer here. We actually can manipulate this value here. Let's say if we have 3 scenarios, epsilon is 1/2. We know we need to satisfy 2 of them. So you can also change this epsilon to 1/3. But here, this is our condition because we actually show that these two conditions are tight. So violating either of them, we are not going to provide the optimal solution for the original chance constraint programs. So the discussion right now is based on the chance constraint programs, and based on our original submission, we also focus only on the chance constraint programs. But the reviewers want us to know, okay, what will happen if we have the Wasserstein distributional robust chance constraint programs. So there are two types of the Wassersteins we are going to talk about. We talk about in our paper, but I am not going to discuss here. So the first one is the type infinite Wasserstein. And based on the literature, we know that the type infinite Wasserstein chance constraint programs can have the corresponding regular chance constraint program correspondence. They have the one-to-one correspondence. So this result is easy. This is easy to extend. So type 1 Wasserstein is slightly kind of complicated, but we can still do the similar condition. We can still do the construction, and this result also holds. But because this one involves more kind of the calculations, we did this one in our paper, but for the presentation purpose, we are not going to show that. So this is the story. Like what we're going to say is the scale CVaR actually can provide us with the optimal solutions. So what will happen for the convex case? And the convex case, the condition is slightly kind of simplified if we have the function G is convex in X and the set X is convex. And then the condition is we only need to have this condition is that we have one X in the deterministic set X such that this constraint is strictly satisfied for the samples. This is the only condition we need. And we still have another condition. This condition is necessary, and we cannot relax this condition. So the proof is still based on, so this proof is based on we take the limit, because right now we have the convex set, and then we take the limit, we say, okay, go to the limit, we still have the result. The reason we go to the limit, you can think about when we have the curve, the alpha actually should go to infinite. What I mean here is this one, our observation is alpha should go to very large when these two curves actually will coincident. So that's why here we are going to take the limit for the convex case. Okay, so this is still to say this problem in the convex sense, these two problems are still equivalent. And right now you may wonder, okay, this problem seems like, okay, you have the alpha here. This problem is very hard to solve. We also do this. We also show that this problem is NP hard to do for the scale CVaR because this is corresponding to the original chance constraint programs. So surprisingly, even though those papers, there are a few papers mentioning about the scale CVaR approximation, but none of the papers actually show the proof for the scale CVaR approximation is NP hard. So we also complete this proof based on our equivalence right now. So this will reduce to the famous paper by Professor Lutke and Ahmed and Nikhauser in the 2010 paper. So this is the most part of the theory part of the scale CVaR approximation. And later on, we are going to tell you, okay, how right now we can use this idea, how we can develop algorithms. Because this problem right now is NP hard to solve, but how we can use this idea to develop new kind of the approximations. We are not going to solve these NP hard problems. We are going to develop some efficient heuristics. So the idea is the first one is the sequential heuristic, because we know we have this kind of the construction, and this construction previously is based on the in the construction proof, we assume we have the optimal solutions. But in general, we don't have these optimal solutions. Otherwise, we don't need to solve this problem. So what we are going to assume here is we are going to assume we will have the corresponding xk, and this xk can be a feasible solution for the chance constraint programs. And then based on our proof, based on the construction, what we will do is we are going to first find the satisfied set, and then we are going to find the alpha bar. This is based on kind of, you can think about this is the violation. And then we are going to do the updating for the scaling factors. We are going to update in this way. So the idea is simple, is if this constraint is not satisfied, and then we are going to keep it. We're not going to scale it. If this one is satisfied, then we are going to do the scaling on the corresponding alpha coefficient. And then based on this kind of the heuristic, so we can show that, so this is the main idea is we are going to update alpha in this way. We are going to split the set into two sets. One part is the solution is satisfied, another part is whether the solution is not satisfied. If it's not satisfied, we're not going to scale it. If it's satisfied, we're going to scale it up. And we're going to repeat this procedure until convergence. So we can show that this procedure is monotone non-increasing and bounded below, and then this is convergent. So very straightforward, we can use the CVaR approximation as the initial solution. So this is the, we call it, this is a sequential heuristic. Later on, we're going to show you the numerical result on the effectiveness of this heuristic. So this is the first heuristic we develop. We also develop another heuristic, and this heuristic is based on the problem structure. Because right now we know this problem is bilinear. So we can use the DC form of the scale CVaR approximation. We can use the fact the 4xy it can be denoted in this way. And then we can do the we can actually write this problem into this way for this part. And then we can take the first order derivative over the negative part term. So we can write down this problem by using the DC, but the drawback here is we are actually going to the second order formulation, to the quadratic formulation. But the idea is very straightforward. We are going to replace it by using the DC, the first order approximation. So this is the basic idea, is we are going to solve this problem by using first order approximation. We are going to repeat this procedure. But notice, very quickly we notice that this problem actually Groby cannot handle it very efficiently because this problem has lots of the quadratic constraints. But we still repeat the previous procedure. We actually show that this one can be monotonely non-increasing and bounded below, and this is convergent. And then the true one we actually use is to combine these two DC approximation and the first sequential heuristic. So what we did is we actually split the set into two parts. If this one is satisfied, we know we are going to do some scaling. So we are going to update the alpha coefficient. Another set is if this is not satisfied, then we just keep the alpha to be 1. We didn't do any scale for the corresponding values. So we borrow this idea into the DC approximation. So what we did here is we only do the approximation, do the first order approximation for those satisfied constraints. If it's not satisfied, we're going to keep it. We're not going to do any update on the corresponding alpha coefficient. So to do so, we are going to actually decrease the numbers of the alpha we need, and Groby can handle this problem in some sense because the problem we test is into a very large scale. We are going to show you very quickly. So combine these two procedures. We are going to separate the constraints into two parts, and then this procedure is still monotonely non-increasing and bounded below and convergent. This one is the one we actually use, and we still use the CVaR approximation as the initial solution. And we actually also test other initial solutions. But for the comparisons, we're actually going to show you they are not comparable. So let's look at a very quick numerical studies. What we have is we have 10 instances from the standard testing library from the Professor Song and Professor Ludke and Singi from the 2014 paper. And then we numerically test the CVaR also X and the scale CVaR heuristic. And this setting, we put the number of the scenarios to be 3000. And epsilon here is to make sure that n times epsilon is not integer. And small n is the dimension of X, and J is the joint chance constraint to say we have 5 pieces. So this is our numerical study. We actually can show that the scale CVaR, this heuristic, can be better than the previous also X. So you can see the improvement actually is not that much because the previous also X is already a very tight upper bound. So to improve on those also X actually is very hard. This numerical study takes us a very long time to do. So we also say those heuristic actually compared with also X is not comparable because in one instances, we have some simple examples to illustrate, but we also have some, in the numerical instances, we also observe the same pattern. In some instances, the also X can be better. So here we only have one instances also X is worse. I think maybe in another sample we have maybe 2 or 3, but majority of the scale CVaR actually performs much better than the also X in terms of the solution quality. So again, this is a very, very tight upper bound, and later on we're going to show you I have another slide to convince you this is a very tight upper bound. So to summarize the scale CVaR story, we have the tight and sufficient conditions for the exactness of the chance constraint programs. We also provide you the efficient algorithms on improving the convex approximations of the chance constraint programs. So I still have some time. So the next story is, remember back to the picture here, we still have another part is how we actually can use those convex approximations to help us speed up the exact method. So I'm going to show you how we can use the scale CVaR is kind of the heuristic very quickly. So solve the chance constraint programs to optimality is very time consuming. And previously I used the 3000, but right now I just use 1000 case to convince you. And each instances I'm going to solve for 4 hours. And this is single chance constraint programs. This is not the joint chance constraint programs. And epsilon is 0.1 and 0.2. And we have 20 instances in total. So after 4 hours, we're going to check how many instances we can solve to optimality. And actually, after 4 hours, we use the big M, and only 13 instances can be solved to optimality within the 4-hour time limit. So the remaining instances, they are still a long way to go. But so what we try to do right now is how we can use those scale upper bound, scale heuristics, those convex approximation upper bounds to help us speed up the exam method. So let's look at those instances, because later on we actually can have the optimal solutions. So we can check whether what's the difference between those heuristics to the optimal solutions. You can say they are very, very close to the optimal solutions. But even though, and we can also find some lower bounds, and those lower bounds are also very tight. So you can see right now, those upper and lower bounds, they are kind of within 1% gap. But right now, if we don't use those upper and lower bounds, it will take us a very long time to solve. So we start to think about how we can use those upper and lower bounds effectively to speed up the exam method. So what we are going to do is we are going to generate optimality cuts. So what we mean here is we have different upper bounds and how we can speed up the exam method. And the tool we are going to use is called optimality cut. So we are going to generate some optimality cuts. And this is based on the previous work with my advisor. And we actually do this by variable fixing. So let's still look at the big M coefficient, big M formulation. The Z here, if Z is 1, that means this scenario is satisfied. If Z is 0, that means this is violated. So right now we have the big M formulation. And Z here is binary. And we're going to generate optimality cuts for Z variables. So what we mean here is like this. Right now we have some easy computable upper and lower bounds. And then we are going to try to add some cuts. So let's say, okay, for the given set S1, what if all the Z variables here are satisfied? So we assume all the Z here are 1. So we add this bound to the easy computable lower bound. It's possible that this restricted lower bound may be greater than the current upper bound. And then if this happens, that means at least one scenario in the set S1 should not be satisfied. So we can generate this optimality cut. This is very easy to compute. And then we can also have another side is we can also add those cuts to the lower bound. If it's greater than the current upper bound, then we know, okay, at least one scenario of them should be satisfied. So this is the optimality cuts. Very simple, very straightforward, but very powerful. So again here, you can see the upper and lower bounds are very important. I'm going to show you one example to convince you that. Let's say we have 5 scenarios here. And Z is 1, that means this scenario is satisfied. Z is 0, that means this scenario is not satisfied. So we can use the scale CVaR heuristic as a current upper bound. And this upper bound will give us the value negative 0.98. And this is the minimization problem. So we're going to try some scenarios. Let's say if we try the scenario Z3 equal to 1, and we're going to find some easy computable lower bound. And this lower bound actually implies the value will be negative 3/4. And this value is greater than the current upper bound. And then we know that what we try here is wrong. So the third scenario should not be satisfied, should be violated. So we can have this optimality cut. On another side, if we try, okay, the 5th scenario is violated. So we are going to put this one here. And we are going to compute either the lower bound, and this restricted lower bound will be greater than the current upper bound. And then we know, okay, the 5th scenario should be satisfied. So you can see this heuristic here actually is very helpful, because if we replace this one with the CVaR approximation, the CVaR approximation actually will be negative 0.59. If you replace this value here, you can say we cannot generate these 2 cuts, because right now this current upper bound is too conservative. So because of this one, we actually can tell you that the higher quality upper bounds are very helpful. So we can go back to those instances and generate the optimality cut based on a very simple corollary. So the idea is like this. For each individual scenario, we are going to calculate its own value, and then we are going to compare it with the current upper bound. If the own value is already greater than the current upper bound, then this scenario should not be satisfied. This is the optimality cut we are going to generate. And then go back to those instances. And then we use one instances and with different epsilon values. And n times epsilon will give us the total number of the violations we can have. And then we can say that the purpose here is to show you, okay, if we use the upper bound of the CVaR approximation, then we can only fix maybe only 20% of the violations. But what if we just replace this upper bound with the scale CVaR heuristic? Then almost like we can fix half of the violations, because right now this upper bound is improved. So based on this very simple observation, what we can show that is we can speed up the exam method. And this is our curve. We can say our method actually can close all the gap within the 4 hours. And here is some simple instances. It might be quicker, it might be faster. So, but in general, our method can close all the gap within the time limit. And again, the discussion here is based on the regular chance constraint programs, but in our paper, we also have the corresponding Wasserstein distribution or robust chance constraint parts. So in summary, today I mainly talk about the convex approximation and the exam method, and we mainly talk about the scale CVaR approximation and on its exactness and some efficient algorithms. So that's all for my presentation. Thank you very much.
Well, thank you very much, Nan, for your very interesting talk. And we have time for some questions. Okay,
Me, I have a question.
this is the first one. David?
Okay, thank you for your very interesting talk. I really enjoy it. This is just one paper. That's the first question. It seems to be a lot of.
I think mainly like the scale CVaR part is one paper, and then this part is another paper.
Okay, that makes much more sense. It's a very huge contribution. Well, but
Thank you.
I have two questions. First, the condition for exactness of your approximation method. The first one, not the convex case. The convex case, I got it. I mean, for each scenario, you just need 1 point fulfilling the constraint. But the first one, this has to be for like almost surely for every scenario. You need a common point. I don't fully understand. Or is the optimal solution that needs to be a strict?
Yeah. So actually, we only need to have this is a very good point. So actually, we only need to have the optimal solution. So because this is based on the construction proof. But what we see here is because the optimal solution is very hard for us to find. So alternatively, what we can provide is okay. If we look at this condition, we assume xi is integer, and then x is binary or x is also integer, and then the right hand side, the b is not an integer. Then if you want to satisfy this constraint, you actually always satisfy it. So
Okay.
again, this is also the question reviewer asks us or try to challenge us is how you can find the optimal solution.
Right.
So again, we only need to have the optimal solution to show the proof, but because we cannot find the optimal solution, so what we can tell is something like this. And then we try to convince people is like, okay, this condition, the strict satisfy condition is not like our first proposals method. Those conditions can be seen in the literature. So this is something we try to convey.
Okay. So, but basically, it's not something that you can check out beforehand. You need to hope for the best. Okay, it's fine. Well, the convex case at least is easier. My second question is this is how strongly based is in the structure of scenarios. Can you export this technique to continuous random variables?
Yeah.
Well,
Actually,
without sampling, I mean. Because of course you can always sample and then you are in a scenario-based situation, but can you directly work with that? I don't know, for example, normal distributions or stuff like that.
Yeah. That's a very good question. So what we try to convince the reviewer is something like this, or in general. So actually, when we start to think about this problem, I think we think about actually this problem is very important. So in the continuous case, it's very hard to justify this case. But this case, in our case, in our we have examples to show this will be tight. So we need to have some margin there. So, but in a continuous case, almost it's very hard to find those cases. So right now for the continuous case, we actually don't know. And one reviewer asked us to do that, but the AE think okay that would be another paper. But
Great.
yeah, I agree. This one is very hard, but because of this condition, we didn't explore that. But it might be interesting to see what will happen for the Gauss case, but we just don't know. Yes.
Okay. Thank you.
Okay, Luis?
Thank you, Claudia. Well, thank you very much for your presentation. Actually, I found it very interesting, very didactic, and I really like it. I would like to ask 3 questions about the first part, mainly the also X and the scale CVaR. With respect to also X, I was wondering how do you compute the inner problem efficiently? Because it's the similar question you answered. In the case of the scale CVaR, you said that you use some DC formulations and some DC algorithms for solving that part. But I was wondering in also X, how do you solve the inner optimization problem? And if it's not linear, how you could deal it? And that's a first question. The second one is that you have in your scale CVaR a convergence in values of the objective function. But I was wondering if there is any hope to have a convergence of the iterates, because you would like to have also a precise xk to stop by instead of only the values of C transpose X. And the last question is the connection in time, because in precision I understood that scale CVaR is better than also X and can beat them. But about time, how they can be compared? That's my question. Thank you very much.
Yeah, thank you very much. Thank you very much. So I think to answer your first question, it's like the also X part. So actually, if you notice that the also X and CVaR approximation, they somehow very similar. So if we just replace the beta here with 0, we just replace the beta. I think you can still see the screen, right?
Yes.
Yeah.
Okay. So, let me enlarge it. So if we just replace the beta here with 0, so this will, the constraint here, what we'll have is we are going to have the truncation like 1 over n, and then the summation of the g is the truncation here. So, so actually, also X also have the similar problems. It's like we are going to solve the hinge loss function. So what we try to convince to the reviewer, to the people, is like, if it's easy to solve CVaR, then it's also easy to solve the OSX. But if the CVaR part is already very hard, then there's no hope we can use the OSX, or maybe the scale CVaR is very hard to improve based on that. So I think to answer your question is maybe based on, okay, our comparison is more like on the CVaR part. So if CVaR is easy, our problem is also easy. But if the CVaR itself is, CVaR is also like the integration problem. If this problem is very hard to do, then take samples will be a feasible choice for us right now. So your second question, yes, I think right now we only have the iterations based on the convergence based on the values, the algorithm we develop. Is based on, okay, this bounded below, so the objective can be convergent, but actually it will take a few number of the iterations. So we also look at whether we can do something there, but right now we don't have the result. But we actually think about how we can do that. I personally have another work, and hopefully I can talk about in the future, is on the distributional robust chance constraint. So we actually can answer your question is how many iterations we can beat the CVaR approximation. So we already have some initial answers, but it's in a different work. The third question is based on the time. Yes, so I for the presentation purpose, I didn't put the time here, but in the paper we should put the time. So actually the time here, the scale CVaR will be much longer than the also X, because we have some trade-off. If we only use the first heuristic, this heuristic is very fast, because this is just update the alpha and then solve the CVaR. But this heuristic is the performance is not that satisfying. So we are going to kind of improve the scaling coefficient by solving the optimization problem. So we are going to introduce the DC, the quadratic form. So that part takes us some time. So yeah, the running time is longer, and even in the linear case. But again, the idea here is to say also X is already a very tight bound, and to beat it is not that easy in these instances. So hopefully I answer your questions, but I know that there are many
Absolutely.
questions.
Yeah, thank you very much. Very interesting work. Thank you.
Thank you.
Emilio?
Okay, thank you very much, Nan, for the nice talk. I enjoyed it a lot. So I have several questions, but I will concentrate only on two of them. The first one is your contribution is based in the representation of the CVaR as an envelope, as a minimum over the time positive of this ReLO function. So my question is, it is possible to use for another, I don't know, approximation of the change constraint, because CVaR is only one that in general is conservative, is well known, but maybe it could be used for another approximation.
Yeah, there's other approximations, performing approximation. Indeed, I think the reason we focus on CVaR is actually there's one paper. So they actually say that. So this paper, they actually say that all the I think they compare another approximation, is performing approximation. They say those approximations are not comparable. So that's why we only pick up the CVaR approximation as a starting point. And also there's another paper to say the scale CVaR approximation is already better than the performing approximation. So that's the main reason like we study or we jump into the CVaR approximation directly. So we didn't consider other approximations because maybe the literature already says something. But I do agree. So we actually do some numerical studies. It's like, okay, it's like something like this. Where, as we mentioned, the also X right now, we can also do the corresponding scaling version. So if we can scale the constraint in the also X, maybe we can also get some improvement. So we just mentioned those things, but actually we can see some numerical improvement, but we don't have any kind of the interesting theoretical result.
Okay, thank you very much. And in this work, you only consider linear functions, so in objective linear functions. So what about the Frank-Wolf algorithm for general functions?
Yeah. So you can say actually we didn't use this C transpose X property at all. So this one can be any functions. So but for our numerical, we just didn't try that, but this can be any functions. Yes.
I see. Okay, no, that's where my question. Thank you.
Thank you.
Okay. If there are no more questions, we'd like to thank you again, Nan, for your talk, and thank you, everyone. And we will